Of course, just as testing all paths through a program is impractical, testing all combinations of input values is also impractical. For white box testing, 100% statement coverage and 100% branch coverage is usually the ideal that developers aim for. And even this can sometimes be unrealistic. So let's turn our attention from code coverage and look at how to design a practical black box test plan. Here is a square root method that takes two floats. One is the number you want the square root for, and the other is the accuracy bound on the result. The specification for this function has a precondition that says n must be greater than or equal to 0, and the accuracy must be strictly greater than 0. The postcondition says that the result is between n minus accuracy and n plus accuracy. Since this is black box testing, we're going to ignore the implementation and look only to the specification for our test cases. The first thing we'll do is create a range diagram for our two inputs and one output. When we have a well-defined range of inputs and output, as we do here, the endpoints of those ranges are boundary points that we can use in our test cases. In addition to these boundary points, I claim that there is at least one more boundary point for the number input, and that is 1.0. Why is 1 a boundary point? Well, we're looking at a square root function, and there's something interesting that happens to the square root of a number at 1. First, the square root of 1 is itself, so that's kind of interesting. But can we say something about the square root of numbers less than 1 versus the square root of numbers greater than 1? If you're not sure, take 5 seconds to try and figure out the distinction, starting now. Ready? The easiest way to see the distinction is by looking at a perfect square that is greater than 1, and then looking at its reciprocal, or 1 over that number, because that number is less than 1, and it's also a perfect square. So let's take 4 and 1 over 4. The square root of 4 is 2, and the square root of 1/4 is 1/2. If you plot these points on a number line, you'll see that 2 is less than 4, but 1/2 is greater than 1/4. And this is the case in general. The square root of a number that is greater than 1 is always less than the original number, and the square root of a number that is less than 1 is always greater than the original number. So 1 is definitely a boundary point. Okay, let's pick a few test points. Notice that these test points tend to be around the boundary values. The next slide gives a rationale for choosing these points. The first 3 points, A through C, are for n, the number that we want the square root of. The next 2 points, D and E, are for accuracy, and the last 2 points, F and G, are for the result. Points A through C are points that are near the boundary points in the range diagram for n. Points D and E are just chosen because they're 2 different accuracy values. You might want to choose something like max value for this just to see if it works, but in this case we did not. Finally, points F and G are chosen as the endpoints of the range for the result. Once we have our points, we can try to arrange them into a test plan. Here we have 3 test cases that collectively use all of our points. The table gives the specific input values, and it gives the expected output as a range. And that's a quick example of how you might come up with test cases when you only have access to the specification. We will revisit these test cases in the next section, which talks about flow graphs.